Hello everyone, welcome to SEG2020 online annual meeting. My name is Fang. I'm interested in developing geophysical tools to solve problems in cities. Traffic is one of the most important issues urban people need to face. In this short video, I would like to show some new observations on traffic and airplane-induced seismic signals. This research is in collaboration with my supervisor, Dr. Yunye Elite Li, Dr. Tiyuan Zhu, and Dr. Ohad Barak. Recently, more and more new seismic acquisition tools, like wireless geophone, distributed acoustic sensing, which also called DAS, has been used for urban monitoring. In this study, we analyzed two datasets, which are recorded by geophone array at the campus of National University of Singapore, and DAS array at the campus of Penn State University. Let's first see the experiment at NUS. At the end of 2019, we implemented a joint geophone and smartphone experiment at NUS campus. We deployed 12 three-component geophone along a campus road. The locations are denoted by these green dots. Three-component means the geophone can measure vibration of the Earth in all three directions at once. In this case, Z component is set vertically to the ground, N component is parallel to the road, and E component is perpendicular to the road. We record 15 minutes data with 1 millisecond time sampling interval and 10 meters spatial interval. At the same time, we have 7 people standing next to the geophone, holding smartphone and recording videos. These geophone and smartphone form an observation array. During our experiment, a civil airplane fly over our acquisition site. Its flight direction is indicated by the blue arrow. Now let's first see what we have recorded at the Station 6. On the top left panel is a piece of video recorded by the smartphone. We extract the audio from the video and plot audio's waveform in the bottom panel. Let's watch the video. So these large amplitudes come from the wind. Here is motorbike signal, car signal, a car going in the opposite direction, another car, and a truck. Finally, we heard the sound from the airplane. On the right panel, we compare the three components of seismic response with the audios on the same event. We can see all these three seismic components show high signal-to-noise ratio on the ground-based traffic. However, from the seismic waveforms, we can hardly identify the signals from the airplane. Next, let's see the characteristics of the traffic signals. These waveforms of the audio and the three seismic components contain 3 events of ground-based traffic and 1 event of airplane. We apply short-time Fourier transform to each waveforms and generate their spectrograms. The spectrogram has vertical axis of frequency and horizontal axis of time. Its amplitude indicates power spectral density, which is plotted in dB. If we focus on the ground-based traffic signals, compared with audio recording, the 3G phone recordings provide better temporal resolution and higher signal-to-noise ratio. As we can see, the traffic events show similar characteristics. Their energy distribute over a wide frequency range. The seismic response of the vehicles occurs only within a very short time when the vehicle is passing through the geoform. So based on these characteristics, we design a method to count the traffic event. Let's take the Z component as example. We first stack the energy in spectrogram within a selected frequency band, like from 100 Hz to 300 Hz, which are denoted by these two white dashed lines. Then we get the red dashed line, whose amplitude can be read from the right axis. Finally, by counting the high amplitude peaks of the red dashed line, we can count the number of the traffic event. Here the number is 3. Then we apply the proposed counting method to the data of whole time. In all, we detected 19 traffic events. From the video, we identify 89 vehicles passing the geoform, which can be seen as the ground truth. The over-detected traffic events were caused by the environmental noise. In this case, the accuracy of the counting method based on seismic spectrogram can reach 95.5%. Compared with one single geophone, a geophone array can provide more spatial information for us. When plot this recording one by one, we will have a 2D profile. Based on the video, we know that the large amplitude events in seismic profile with tiny dip are mainly caused by the moving vehicles. We zoom into a small piece of window and filter the data into a narrow frequency band, which is 25 to 70 Hz. We convert the vertical axis to the distance. There are 3 cars past our array during this time window. In the profile, we observed 3 groups of energy moving along the array. Using the travel time and the distance, we can estimate the average car speed, which is 76 km per hour. Next part, we focus on the airplane signals. This profile shows the airplane-induced ground motion recorded by the seismic Z component. We can see a group of energy from airplane propagates along the array. Taking the channel 0 as masked channel and applying cross-correlation between the masked channel and other ones, we can get the cross-correlogram on the right panel. By linear fitting the arrival time of the airplane's main energy, we can get its apparent velocity along the seismic array, which is 1,308 meters per second. It is very large because of the angle effect. Now go back to the spectrogram of one single geophone. To our surprise, the airplane signal, which seems to be undistinguished in the time domain, is clearly visible on the spectrogram of all the 3 seismic components. We can identify 3 order harmonics of the airplane. Affected by the Doppler effect, the received harmonics shift from the high frequency to the low frequency. Since the airplane was flying at an altitude of several hundred meters, the sound wave mostly impacted vertically. Consequently, the ground motion is stronger on the vertical component than in the 2 horizontal components. The Doppler effect is used in some types of radar. to measure the velocity of the detected objects. Now, I will show how to use the Doppler effect to obtain flight parameters of the airplane with seismic data. From this formula, we know that there is a frequency shift between the observed frequency f and the emitted frequency f0. This frequency shift is determined by the velocity of the airplane, the speed of the sound in air, and the angle of alpha. Here, alpha is defined by the angle between the vector of the speed of airplane and the line between the airplane and geophone. Let's first consider a case when alpha equal to 0. The figure on the right-hand side shows the Doppler effect of an airplane moving in a constant velocity at different altitudes. When the airplane is coming towards the geophone, the observed frequency f is larger than the emitted frequency f0. When the airplane is away from the geophone, the observed frequency will become smaller than the emitted frequency. Let's consider a more realistic situation. In a 3D case, the seismic array is deployed on the ground surface XOY plane. The airplane is flying at a certain altitude and at a constant velocity of v. The angle between the projection of its flight direction on the ground and the seismic array is theta. For a certain geophone, the angle of alpha is in the plane defined by the geophone and the flight line. D is the distance between the airplane and the geophone. D and alpha change with time. By defining flight distance S and the closest distance between the geophone and the flight line H, we have this formula. Here, all these unknowns are constants. Using nonlinear curve fitting, we can fit the Doppler effect obtained in the seismic data with this formula and estimate these unknowns. The estimated values are listed in this table. I want to emphasize that the first 4 parameters can be obtained with only one geophone. Flight direction theta can be estimated by using the apparent velocity, which can be calculated from the cross-correlogram. After consulting a professional pilot, we believe that these obtained flight parameters are within a reasonable range. Now, let's see another case of airplane signals recorded on DAS data. Penn State DAS array uses a 5 km of pre-existing dark telecommunication fiber, which is lying in concrete conduit at a depth about 1 meter. The data recorded by Selexa IDAS2 interrogator unit with 2 meters channel spacing. There is a small airfield 5 kilometers north of the site. From the data recorded at channel 300, we observed Doppler effect of the airplane, which is similar to the geophone signals. We can also get these flight parameters by fitting the Doppler effect. These estimate parameters are all within reliable range. As conclusions, in this research, we demonstrate that geophone and DAS array deployed in cities can record the ground motions induced by ground-based traffic and airplane. We can use geophysical methods to extract many useful traffic parameters, which describe the traffic situation and flight status. Our research reveals the potential new applications of geophysical tools for traffic monitoring and airplane tracking. Okay, this is the end of my presentation. Thanks for your watching. If you want to know more about our research, please visit our website and feel free to contact me, and I would like to answer any questions from you.